Hello all, welcome to this course on time series modeling and forecasting using R. Now, as you see in front of you that we have a practical session today, and then the focus of this practical session would be just to sort of work out the details using a real data and maybe through a simulated data and try to connect that using whatever theory we have learned so far in this week. Okay. Now again, if you're seeing this particular video after a long time, then just to very quickly brush upon what exactly we've covered this week so far. So the main focus for this week was a different kind of a time series model called as ARFEMA process, right? And as we discussed much earlier, that ARFEMA stands for autoregressive fractionally integrated moving average, right? Now, firstly, you should understand that what exactly is the difference between, let's say, an ARFEMA process as compared to ARIMA or SARIMA. So, back when we studied ARIMA, so ARIMA stands for autoregressive integrated moving average, and necessarily when you talk about ARIMA, that differencing operator or the differencing order, which is D, that has to be an integer, right? And then we sort of difference, let's say, once or twice or thrice and so on, and then the D stands for the number of times we difference the series. Now, when we slowly transition into ARFEMA processes, then the differencing operator could also take some decimal values, right? And as seen in some of the previous lectures this week, that the value of D sort of tells you that how persistent a time series is, right? Now, if you remember, the whole idea about discussing ARFEMA processes is that you want to capture the persistence in the underlying time series. And what exactly is persistence? So, persistence is nothing but whether a time series possesses some long memory properties, right? So, just to take a very quick example, so let's say if you are sort of analyzing a stock price of, let's say, Reliance or TCS or whichever company, then let's say suddenly some random shock comes and then you can see a sharp movement in the stock price, right? Now, does that movement last for some while, or does the series again reverts back to the mean very quickly? So, if that sort of effect lasts for some while in the future also, then we say that the underlying time series is persistent. Or exactly opposite to that, if the series or if the stock price sort of reverts back to its mean, then we say that you have some anti-persistent nature. Okay. All right. So, before we start with the actual coding, so you require, as always, you require some packages, and then you want to import some libraries, right? And if you're following our practical sessions which we take every week in R, then you must remember that you obviously have to install all these packages if not done already. So, let's say forecast, then fracdiff, right, and then T series, and then URCA. Okay. Now, by the way, these packages would be required to sort of manipulate or sort of implement the underlying functions that we will soon run in this particular code, right. And I think as of now you must be familiar with forecast and then T series, right. So, forecast and T series are kind of predominant packages that one has to apply or one has to import when you're trying to analyze any practical time series data. Okay. So, again let's do that. And now again just a very quick refresher, if you sort of forgot that how do you install the packages. So, again one can go to tools here and then click on install packages, and then a couple of things to sort of take care of here, that you want to make sure that this thing says repository. So, if not, then you want to select repository, because repository stands for that it will search online from its online repository, and provided that you have a valid internet connection, it will sort of download the package and then install that. Okay. And then whatever package name you want, you can actually input it here, for example, forecast or fracdiff or T series, etc. Right, and then simply click on install. All right, and once you install, don't forget to bring the packages inside the R environment using a library command. Okay, so we'll do exactly that now. So, let's say library forecast, then library fracdiff, right? And again, just notice that since this is the console, then once you hit library on any command or any package name, then R sort of runs a very simple sort of a command so as to just bring the package inside the R environment. Okay. Then the second one is fracdiff. Now, fracdiff stands for fractional differencing, because this entire idea about ARFEMA is that the differencing order D can also be a fraction, right. So, we hence call it as a fractional differencing order or fractional differencing parameter. All right. So, we require this fracdiff library and then T series. So, T series stands for time series, and then URCA for some of the other functions that are there in this code. Alright, so once you make sure that all the libraries have been installed, now the next thing is you want to sort of run this. So set seed 1, 2, 3. So set.seed is a function that sort of tells you that every time you try to replicate this code or try to reiterate the code, then it should actually give you some random values and not the exact values that you have in the first iteration, right? So this just tells R that every time you sort of simulate the same code again and again, then every time it has to randomize and then start the entire process again, okay? And what number you should input here really doesn't matter. So this is just a random number. So 1, 2, 3, we're just putting some random number inside this set.seed. And here also you can see that for reproducibility, so if you want to reproduce the code again and again, then you have to ensure that every time it should be completely a random sort of an environment, okay? Alright, so set.seed 1, 2, 3, and then the next thing we'll fix is we'll fix some orders now. So the first thing is we'll fix some n. So n in this case is 1000, which is number of observations, right? And then the value of d. So d we are taking as 0.3 here, right? And then d stands for nothing but the fractional differencing parameter that you have in the RFEMA structure, okay? So d is 0.3. Now again, you can sort of play around with this code, right? So since you have access to all the codes, a very, very strong suggestion is that not just running the same code that we're discussing in class, but then how do you play around? So let's say change this value. So let's say 0.6 or 0.7, something like that. Or you can even take negative, right? If you remember, one of the lectures in this week was predominantly based on for what values of d do you have, let's say, long memory property or short memory property, stationarity, non-stationarity, persistence, anti-persistence, right? So by playing around with the value of d, you can actually pinpoint to the particular case that we studied in the theoretical section in this week, all right? Okay, so now developing further, so since RFEMA process requires the AR components and the MA components as well, then we can actually fix some AR coefficients. So AR coefficients in our case would be 0.5, and this is nothing but AR1 structure, right? So you can run this and then MA coefficients. So MA coefficients we are keeping to be 0.2. Now again, you can again play around with all these values. So probably change this 0.5 to let's say 0.9 and then see what different thing you're getting, right? So this is a very basic idea if you are kind of really starting off with some hands-on kind of an exercise, right? I mean, whatever code you have been given with, don't just blindly run that and then try to emulate the results. I mean, try to play around with some of the values, right? So for example, what would happen if you change this 1000 to let's say 5000? What would happen if you change this 0.3 to let's say 0.7? Because then 0.7 would exceed 0.5, right? And then it might happen that you have an entirely different sort of a RFEMA fit, okay? Or what might happen if you change the coefficients here? So let's say from 0.5 you take a very, very small coefficient, let's say 0.001, right? So all these things could be sort of tried out. So due to time crunch, we can only focus on one particular case, right? But then it's your task to sort of emulate the same results by mixing and matching the parameter values here, all right? So hope this point is clear. And then again, this is not just for this particular code, but then all the previous codes and then the codes to follow also, all right? Okay, so once we fix all these values, then now the next thing is to sort of simulate a particular RFEMA model, right? So we'll give it a name as RFEMA underscore SIM. And in R, once you import some of the libraries we saw earlier, then this is an inbuilt function. So frag diff.sim. Now again, as discussed earlier, if you simply hover over a particular function, right, it sort of tells you the entire syntax. So can you see that? So what exactly goes inside the frag diff.sim function, right? And then you have to specify the AR component, MA component, etc. So you have a lot of things, right? So here we'll specify n, which is sample size, then d equals d. So d is the fractional differencing parameter in our case, and then AR would be the AR coefficients, and then MA would be MA coefficients, right? So needless to say that even though you see a lot of different things inside that fragdiff.sim command, but then we have to keep it simple, right? So what are the ingredients that one requires to sort of model the RFEMA process? These are the specific ones. So n, d, AR coefficients, and then MA coefficients, okay? So now we'll run this line, okay? So again it says that object MA coefficients not found. So probably we again go back here. Now again to make sure that if you get some error like that, so again make sure that that particular line has been run, okay? Alright, so now the MA coefficients have been run. Now again, if you go back to rfema underscore sim, now it should work. Okay. So this is again sort of what do you call? So looking at the errors that are there in the console and then working accordingly. Alright. Okay. So once you fix or once you sort of model this or fit this rfema process with these parameters, then we can actually see a plot of that. So plot of the fitted rfema series, and this is exactly how the plot looks like. Now again, let me zoom in for you. So this is a zoomed plot. So this is nothing but a simulated rfema process with those parameters. So D is 0.3, then AR coefficient, MA coefficient, etc. Right. Now again, if you repeat the same exercise again the second time, you should get a completely different picture. I mean, it should be similar, but then all the values would be different because this is a simulated sample, right? So every time you run the code, you should actually hope that the next iteration you will get a different sort of a sample. All right. So hope this makes sense. Now let me close this and again come back to the code. Now what we want is we want to estimate the rfema model, right? We want to estimate the rfema model. So you have a command called as rfema. So we'll apply this rfema command on the fitted rfema series, right? So rfema applied on rfema underscore sim $series. So let me run this now, and then we'll give it a name as rfema underscore model, right? So this structure here, so rfema underscore model, this sort of contains the fitted or the estimated rfema model. Now how do you extract, let's say, the parameter estimates or something like that? I mean, once you are estimating anything or once you are estimating a model, the first thing is that you want to extract the estimated parameters, isn't it? So for that you can actually use this summary command. So summary applied on the fitted model, so rfema underscore model, and you can actually see all the fitted coefficients in the console. So this is what the output is. So you are trying to fit an rfema structure, then what are the estimates of, let's say, D, then the AR coefficient, MA coefficient, etc. Okay. And further it also tells you, let's say, log likelihood, then AIC, etc. Okay, makes sense? So this is more like a fitting exercise. So given a simulated data coming from an rfema process, how do you fit or how do you estimate the underlying parameters of the rfema model, right? And now here one important thing to note here is that the estimate of D, if you look closely, is 0.2824, which is very, very close to the value we are fixing already. So if you remember what was D that we fixed, so the value of D was 0.3, isn't it? So this 0.2824 is close to the assumed value, which makes sense, all right. Okay, so now that we have fitted a particular rfema model, then we have to actually check and then go ahead and then do the diagnostic checking. So once you fit any time series model, be it AR, MA, ARIMA, rfema, whatever, then the very next step is to sort of ensure that all the assumptions of the model are being met or not, right, in terms of the residuals. So what exactly are the assumptions? We've covered in depth in some of the earlier weeks, right? If you remember, the whole idea about diagnostic checking is exactly this. So normality of the errors, then independence of the errors, then the variance of the residual should be constant. So all these are the underlying assumptions which we want to check now, all right. Okay, so the command that you see in line 27, right, this is PAR and then MF row equals 1, 2. So if you want to plot multiple plots in the same window, right, then you actually have to use such a command. So this tells R that I want both these plots, ACF and the PACF, in the same window, or rather in a same row, because this is 1, 2. So single row and 2 columns. So you'll essentially get plots which are side by side, all right. So we'll run this, and then what we'll do is we'll run the ACF of the residuals and the PACF of the residuals, right. Now again, let me zoom the plots for you. So these are the ACF, so ACF on the left hand side and the PACF on the right hand side. Now again, interestingly, you don't see any correlations which are highly significant. I mean, of course, apart from this right here, right, but apart from that, all the other correlations are in between the bounds, which means that they are not significant, which also means that there is no autocorrelation among the residuals, right. There is no, and then again, the other part to note is that you don't see any patterns among the spikes also, right. So this is one very important way of checking if the assumptions are being met or not, by simply plotting the ACF and the PACF of the residuals, all right. Okay, and then the next thing is you'd want to check for stationarity of the residuals using the KPSS test. So again, if you remember the KPSS test, we've covered this long back, but then one can actually implement this KPSS test to check in fact whether our residuals are stationary or not, because we don't want any non-stationarity among the residuals, right? Because residuals should be completely random. So they should be, in other words, they should be stationary. So how do you check that? We can actually implement this KPSS test on the residuals, and then let's see what the output is. Now again, here it says that could not find the function ur.kpss. Now again, let me go back and then try running this urca one more time, okay, and again come down to KPSS test here, right, and now it has run, right. And why is that? Because this command ur.kpss is there in the urca package. So if for some reason your urca package did not load correctly in the first time, now again go back and then try installing the package and again loading that in the R environment one more time, okay. Makes sense? So now this is passed, and then now summary of the KPSS test. So this is exactly the KPSS test. And then here it sort of gives you the value of the test statistic, so 0.0461, and all these are the critical values. So 0.347, 0.463, 0.574, and then 0.739. So here if you see, this 0.0461 is less than any of the critical values that you see here, right, which means that the value of the test statistic is lesser than the critical value, so you fail to reject the null hypothesis, isn't it? If the value of the test statistic exceeds the critical value, then you would reject the null, right. But if the value of the test statistic is less than any of the critical values here at whatever percentage points you take, so you fail to reject the null, and the null hypothesis in KPSS is that the underlying residual series or underlying whatever series you are testing for is indeed stationary, okay. So here the conclusion is, since you are failing to reject the null, you actually go with the fact that the residuals are indeed stationary, okay, which makes sense also, alright. Okay, so once you sort of do these preliminary diagnostic checks, then you can actually go ahead and then do the forecasting. So the first thing is you specify some forecast horizon. So let's say I want the forecast 20 time points down the line in the future. So forecast horizon is 20 in my case, so let me run that. And then again you sort of bring this command forecast from the forecast package. You apply on which model? You apply on the RFEMA fitted model, and then here you specify the forecast horizon. That's it, right? And then we'll give it a name as RFEMA underscore forecast. Make sense? So running forecasting is not a tedious task. So just a couple of lines, right? Now the whole idea is that how do you visually check if the forecasts are making sense? So you can actually plot the forecasts, right? So these are exactly how the forecasts look like. So again, if you notice here, some strange thing is happening, that even if you run the single plot command, again R is thinking that there will be one more plot here which should follow, because remember that we applied this PAR command earlier, and then we specified that I want 2 plots in a single row. But now we don't want, right? I mean, now we don't want. So what one can do is one can change this 2 to, let's say, 1 again, alright. So I want a single plot in a single row and a single column. So run this, and then again if you come down and then run the RFEMA forecast plot, now it should give you the complete plot in a single window. Make sense now, hopefully. So let me zoom in now, alright. So this is the RFEMA fit or the fitted model, and then the line in the blue that you see. So let me again zoom in. So the line in the blue that you see towards the end is nothing but the forecast, right. Now a couple of conclusions one can make is that it's at least capturing the trend aspect, isn't it? I mean, you're not seeing a horizontal line for sure, right. So it has a tendency of capturing the trend aspect, of course. So in a way it might make sense, okay, makes sense. Alright, and then now the next thing is if you want to save the results to some CSV file, let's say, right. So we can do it. So let's say results and then data frame, and then you mention the timestamps. So 1 to whatever length of the series you have, and then the value that has to be outputted as a second column in that CSV file. would be nothing but the actual Arifima fitted series. Alright. So, probably I will not run this because I do not want an CSV file to be created on my desktop, but then if you want a separate CSV file where you have two columns, the first column tells you the timestamps and then the second column tells you the actual values of the fitted Arifima model. Then you can actually run this results and then write.csv command. So, write.csv command, then there inside you input the results, comma, you have to give it a name. So, I will give it a name as Arifima underscore simulated underscore data.csv, right, and then row name is equal to false, right. So, this is the syntax. Okay. Now, let us say what if you want to simply print out the fitted coefficient. So, if you are not interested in any of the other stuff that the summary command gave us earlier, if you are only interested in seeing the fitted coefficients of the parameters, then you can actually do something like this. So, you can give it a name, let us say estimated Arifima model coefficients, and then you want to simply print out the coefficient part from the Arifima model. So, this is exactly what you will see. So, this is what your D is, the estimated D is, right. This is the estimated AR coefficient and this is the estimated MA coefficient. Make sense so far? Okay, so now the last thing we will do in this code is to sort of implement the Arifima process on some real data, because otherwise how would you figure out if the Arifima process is indeed making sense or not, right. And for that matter, we will again use the air passengers data that we discussed earlier. So, we have been again using the same air passengers data again and again just to sort of keep some consistency. So, if I bring in some random data every time, then there would not be any connection as to what is going on in that particular session as compared to what we studied in some earlier practical session and so on. So, if you keep a practical data which is consistent throughout, let us say explaining all sorts of models, then at least you will try to find out that what model is better to fit that or what model might not be very good model to fit that and so on. Make sense? So, again air passengers data, I think probably almost all of you should have some idea about what this data means, right. Okay. But again, if not, then as discussed in the last code also, you can always type in, let us say question mark and then air passengers, okay, or probably we will do it now also. So, let us say, so you load in the data first, right. So, data air passengers, then you give it a name. So, let us say y is the data which is air passengers. And then again, like I said, if you want more information about any function or any underlying data set, then you have to actually do question mark and then type in the name of the data. So, air passengers and then hit run, okay. And over here you see the description of the data set, right. So, do you remember this data? So, we have been using this data multiple times already. So, this is the monthly airline passenger numbers from 1949 to 1960, and then sort of gives you a small description and then the source of the data. So, this data set is from Box and Jenkins airline data, and then again between 1949 to 1960, and then this is a monthly time series in thousands, right, and this is exactly the source. So, it sort of dates back to 1976 from this book by Box, Jenkins and Rinzel. So, time series analysis, forecasting and control, the third edition, okay. And then down the line it sort of gives you some examples that you can sort of implement using this data set. So, here let us say ARIMA model. So, if you want to fit some ARIMA model, right, and then this is sort of, it tells you some examples that can be hands on just to sort of start the coding with using this air passengers data, alright. Makes sense? Now, again, so we will use this data here for our purpose. Now, the very first thing to do is to plot the data. So, let us say you have a simple plot of the data and then this is exactly how the plot looks like. Now, again remember that this is a very classical data set that people use for explanation purposes because it contains a trend, seasonality and changing variance. So, all sorts of non-stationarity behaviors can be seen in this air passengers data. Make sense? Okay, now the very first thing is we want to check if the data set is stationary or not. So, we again apply the KPSS test to check for stationarity and then this is the summary, alright. And again here surprisingly, again if you see the value of the test statistic is 2.739 and then 2.739 is much higher than any of the critical values that you see here, right. So, the maximum critical value is 0.739 right? So this 2.739 is way above any of the critical values. So what do? So you reject the null, right? And then you go with the alternative, and then alternative hypothesis under the KPSS test is that the series is not stationary, right? So the null hypothesis is that the series is stationary, and then the alternative is that the series is not stationary. So if you are able to reject the null, then it sort of means that the underlying series is not stationary to start with, all right? Okay, then how do you handle? So the next thing is you sort of difference the series. So if something is not stationary, the very first thing you should do is you should apply some differencing. So we can difference the series once, right? And here again you can check for the KPSS test, right? So you can again imply or you can apply the KPSS test on the different series now to check if the different series is stationary or not. Or as we have done earlier, you can actually go for creating the ACF plots and the PACF plots of the actual different series now. Okay. So ACF of the differenced y and then PACF of the differenced y. Okay. Now again here I want two plots side by side, so I have to specify using a PAR command, right. So the first is ACF, second is PACF. Let me zoom in both the plots for you. And these are the ACF structures and the PACF structures. Now here clearly you can see that even after first difference, the series are not stationary, right, because you see some repetitions here. Can you see that? So you have lots and lots of correlations which are outside the bounds, which means that you have some autocorrelation among the lags as well, right. And then there is some seasonality also, right. So because you know that from the initial plot of the series we can spot the seasonality, and also from these two plots you can actually plot the or spot the seasonality. Okay. So can we go ahead and then try to model this using an RFEMA model? So this is the question. So we can try. So let's say RFEMA underscore model would be RFEMA applied on y. Now one thing to note here is that we are applying RFEMA not on the different series, but then on the actual series, which is y, isn't it? Now the summary of the RFEMA model. So this is the summary of the RFEMA model. So what's your D, then what is the AR coefficient, right. So here if you notice, see R is sort of estimating an RFEMA model fitted on the actual air passengers data, and then it's telling that the value of D should be 0.47. There should be two orders in the AR part, so AR1, AR2, and then there should be a single order in the MA part, and then these are the coefficients, right. And again it sort of gives you AIC value, log likelihood value, etc. Okay. And now diagnostic checking. So we sort of repeat all the steps that we've done in the simulated data. So let's say ACF of the residuals and the PACF of the residuals. Now again let me zoom in. So these are the ACFs and these are the PACFs. Now again clearly you can see there are some repetitions, right. So can you see the repetitions, or not the repetitions, but can you see significant spikes at lags 12, 24, probably 36, etc. So this is a very strong indication that there is seasonality present, and you have a monthly seasonality, right. So whenever you have a monthly seasonality, such tendencies could be seen in the ACFs and the PACFs, all right. And then KPSS test applied on the residuals. Now we'll see what happens, right. Now here the value of the test statistic is 0.72, and surprisingly 0.72 is bigger than this 2.5 percentage point, right. Even though it's slightly less than 1 percentage point, but then it's bigger than this. So we can actually reject the null and then again tell that the series is indeed non-stationary to start with, right. But nevertheless, since we are fitting an RFEMA model, so we can actually go ahead and then try to forecast that. So forecast horizon would be 12, which means for the entire next year or 12 months, okay. And then you implement the forecast command on the fitted model and then plot the forecast. Let's say if you want a single plot comprising of the or spanning the entire window, then you again go back here and then try to change this to 1, 1, right. Now again come back here and then try to plot this one more time. So this is the forecast plot, all right. And then here you can clearly see that the forecasts are not making very good sense, right, because you would want to preserve the seasonality aspect, but then you are seeing that you are getting a straight line almost, right. So in a way the RFEMA model is not doing very good here, Okay, so this is the conclusion. But again, this is just to tell you that how do you implement, let's say, a fitted RFEMA model on some real data down the line. So if you think that there is some long term or let's say long memory underlying in the series that you have, or there is some persistence in the underlying series, then you should actually go with fitting the RFEMA model, and then hopefully the forecast should make sense. But for this data set, which is air passengers, it may happen that air passengers, the tendency of monthly air travel is not persistent, right? Because again, clearly you can see that even if you have a trend, but you have seasonality also. So whenever you have a spike, it sort of gets back to its mean very quickly, right, due to seasonality. So you don't have any persistence in the time series, but this was just an example to tell you that how can one fit a RFEMA model on a simulated data and a real data. All right. Thank you.